In our last video, we broke down the mechanics of separating messy mixtures. We used gravity to decant sand, harnessed boiling points in distillation to save pure water, and even spun liquids at high speeds in a centrifuge to separate heavy particles. But what happens when liquids blend completely together, or when a mixture contains several different components? Welcome to Part 3. Today, we're leveling up our chemistry toolkit to tackle immiscible liquids, fractional distillation, paper chromatography, and multi-step separations. Let's jump in. It is one thing to filter out chunky, heavy particles like sand. It is entirely different when facing liquids that seamlessly combine into a single uniform fluid, or dry powders that are thoroughly tangled together. You have to figure out how to pull them apart without accidentally destroying their chemical makeup along the way. As these mixtures become more complex, we have to graduate from simple physical filters. We have to start leveraging the precise physical properties of the molecules themselves to force them apart. Let's start with a scenario where liquids outright refuse to mix, what chemists call immiscible liquids. Think of oil and water. They might be trapped in the exact same container, but they remain strictly separated by their different densities, with the lighter oil floating on top. To exploit this natural boundary, we use a specialized piece of glassware called a separating funnel. Because gravity naturally sorts the two liquids into distinct layers, we can manually isolate them. At the very bottom of the funnel is a small control valve known as a stopcock. We turn the stopcock to slowly drain the heavier water out the bottom, and then quickly pinch it shut the precise millisecond the lighter oil reaches the exit. When liquids naturally repel each other, gravity and basic density give us the easiest, most efficient method of separation. But the difficulty ramps up when we encounter miscible liquids. These are liquids like rubbing alcohol and water that dissolve into one another completely, forming a seamless, uniform blend. Gravity won't help us here. Instead, we have to exploit the fact that these two liquids boil at completely different temperatures. We do this through a process called fractionating distillation. We heat the mixture in a flask attached to a tall glass tube called a fractionating column. As the mixed liquids boil into vapor, they rise into this column, undergoing dozens of rapid cycles of condensing back into liquid and re-evaporating into gas. This constant back and forth is what makes the fractionating column so incredibly precise. The column naturally gets cooler near the top. The liquid with the higher boiling point quickly cools off and drips back down into the flask, while the vapor with the lower boiling point successfully escapes out the top to be collected. Oil refineries rely on massive, towering fractionating columns to process crude oil. They continuously boil and sort the crude into highly specific fuels like petrol, diesel, and kerosene, based entirely on those slight differences in evaporation points. By harnessing thermodynamics and controlling the temperature gradient, we can literally boil a perfectly unified liquid back into its original individual parts. The complexity scales even further when we move past liquids and look at solid mixtures with 3 or more components. Imagine a chaotic pile of powder containing iron filings, sand, and iodine. You cannot apply a single technique to fix this. You need a sequential game plan, and the exact order of your operations is critical to avoid destroying the ingredients. We absolutely have to extract the iron first using magnetic separation. If we skip this and apply heat too early, the high temperatures will demagnetize the iron filings, ruining our ability to easily pull them out of the sand. With the iron safely removed, we can heat the remaining sand and iodine. Iodine is a sublime solid, meaning it turns directly from a solid into a vapor when heated. The purple iodine gas rises out to be collected, leaving only the heat-resistant sand untouched in the dish. Separating a complex mixture is a strategic puzzle. Applying the right physical forces in the wrong order will ruin the entire experiment. Finally, we face the microscopic challenge, separating a mixture that looks like a single uniform substance even up close. A single drop of black ink, for example, is actually a blend of several different colored dyes. To pull these invisible blends apart, we use paper chromatography. This technique relies on 2 distinct components: a stationary phase that stays absolutely still, and a mobile phase that moves through it. The stationary phase is typically a specialized piece of cellulose filter paper. The mobile phase is a liquid solvent, like water or alcohol, that travels across that paper. We place the bottom edge of the paper into our solvent. Through a process called capillary action, the liquid defies gravity and creeps upward through the paper's microscopic fibers, eventually washing right over our ink and dissolving it. The different dyes in the ink have different levels of chemical attraction, known as affinity. Constituents highly attracted to the moving solvent will race ahead toward the top of the paper, while those that prefer clinging to the stationary paper will drag behind. This makes chromatography incredibly useful in the real world. Lab technicians use it to separate complex amino acids, detect specific hormones, or screen for pharmaceutical drugs in urine samples. Even when a mixture is tightly bound at the microscopic level, tiny differences in chemical affinity will force its hidden components to reveal themselves. Chemistry is defined as much by the surgical mastery of physical properties used to take the world apart as it is by the reactions used to build it. It is the art of recognizing and exploiting the invisible rules governing every molecule. So, let's put your new toolkit to the test. Imagine you're handed a single beaker containing a mixture of iron filings, water, and rubbing alcohol. Based on everything we've covered today, what exact sequence of separation techniques would you use to safely isolate all three of those materials? And crucially, what must your very first step be? Let me know your step-by-step game plan down in the comments. If you enjoyed leveling up your chemistry skills today, be sure to like, share, subscribe, and ring that notification bell so you never miss an episode. See you next time.